Hi, this is my video number 34. I'll talk on the mellin transform. In the previous lecture, I've talked on the Fourier transform and Laplace transform, and now on the mellin transform. Alright, so again, I just read whatever in the notes. Where necessary, I will do some writing. Okay, so the mellin transform is extremely useful for certain applications, including solving Laplace equation in polar coordinates as well as for estimating integral. So if you consider the generalized Laplace transform, so suppose for a finite t, a function gt is absolutely integrable on 0t, which is given by that. This means the function gt is absolutely integrable on the limit 0 to t. And we have gt of order exponent alpha t. Wrong typing again there. As t goes to infinity for some real constant alpha, then the one-sided Laplace transform is given by this. So we consider only 0 to infinity. So this is inside the definition of the Laplace transform. So this provided g is absolutely integrable, then those Laplace transform is absolute converge and holomorphic in real of s greater than alpha. And similarly, if you suppose the integral gt also integrable, and gt of order exponent of beta t as t goes to minus infinity for some real constant beta, then one-sided Laplace transform, you have minus infinity to 0. You can just change to 0 to infinity. So we have that. Converge absolutely in and it is holomorphic in the left half plane real of s less than beta. So under the same condition gt, which is gt is absolute integrable, and if beta greater than alpha, then the two-sided Laplace transform we obtain as that. Okay, and this converge absolutely is in and holomorphic in the vertical strip real of s between alpha and beta. So if beta less than alpha, then the generalized Laplace transform does not exist for any s. So this is quite obvious if you substitute it there. So suppose beta is greater than alpha, and let t as a minus log of x, which gives us gt as a g minus log. So we take this as a fx. Then note that you can just substitute e minus st, t with minus log x, then you can have x to the s. So if you substitute all this thing into our Laplace transform, so we have this. You just substitute everything in there, so we have this, and this is the definition of the mellin transform. So this is the definition of the mellin transform. So where m is the mellin transform of fx. Remember that our fx, we substitute x with that x, t is with minus log x. So the mellin transform of fx is two-sided Laplace transform of gt, where t is minus log x and is converged absolutely and is holomorphic in the strip real of s between alpha and beta. So if you consider this example, gt is minus alpha absolute of t. Excuse me. Then the Laplace transform of that integral, of that function, you can just substitute there. So it is not difficult to find. Of course, in this case, you have 1 over s plus a. Okay, so provided that real of s greater than minus a. And similarly, we consider the other half minus infinity to 0, where we approach t from a negative side. Right? Everything inside is from the Laplace definition of Laplace transform. You can just evaluate. This is again typing error. So it should be minus infinity to 0. Then you have a1 over a minus s for real of s less than a. So thus the mellin transform converge and analytic in the strip of that. So remember that the relationship between mellin transform and the Laplace transform. So that's why we're looking for the Laplace transform. So the definition, the relationship between the Laplace transform and the mellin transform, we have it here. So the second example, this example. So if you consider gt as e to the plus, plus at, then g plus s, the Laplace transform, is 1 over sa. And for the negative, the other half, the Laplace transform of eat is 1 over a plus s for s less than minus a. So if you consider that t as a minus log x, which give you, you can have the mellin transform, you can see that from there, as the limit goes to minus infinity, the function doesn't exist because it involves log. So in this case, mellin transform doesn't exist. Now, since gt is of order exponent alpha t as t goes to infinity, so what we obtain, if you substitute again like with t minus log x, so fx is of order x minus x minus alpha. You just substitute t in that, so you have this as x goes to 0 from positive. And also gt of order exponent beta t as t goes to minus infinity. Alright, and so we have fx of order x to minus alpha xx sx tend to 0 from positive. So what we can see from this behavior is that when the mellin transform of fx exists, its strip of analyticity is determined by the behavior of fx. As x goes to infinity, fx goes to 0 from positive and x goes to infinity. So the inversion formula for the mellin transform follows from the inversion formula for the two-sided Laplace transform. So this is from the Laplace transform. This is for the inverse of the mellin transform. Okay, so this part here is to say the relationship between the mellin transform, the behavior of the mellin transform can be determined by the behavior of the function fx itself. Now for the inversion of mellin transform, we have so we have this, where we require that c in between alpha and beta, so putting x equal to minus log t in the Laplace transform. So we have this. So this gives you the inversion of the mellin transform. All right. Now look at the theorem down here. This theorem provided without proof. Okay, suppose fx is a function of the complex variable s gamma plus I tau, which is regular in the infinite strip alpha a and b, and that for any arbitrary small positive epsilon, fx tends to 0 uniformly as tau goes to infinity in the strip, then if the integral converge absolutely for each value of gamma in AB, and if for positive real values of x and a fixed and a fixed c in AB, so we define this, then in the strip AB, so we have this. So if you remember, this is the from the previous page, I think this is the definition of the mellin transform. Now look at the example down there. So if you consider fx as e minus ax, where a positive, all right, then the mellin transform, this is from the definition, you can see x s minus 1, our fx is a minus ax there, all right. You can write this by using that substitution uax. If you use substitution uax, you can write those terms as that, and obviously this term here is the a gamma function given by that. This is the gamma function. So we have a gamma s tau s a to s. So this is the tau s is the gamma function. Okay. And next example. So if you consider fx as 1 over e exponent x to minus 1, then the mellin transform of f is given by this thing. Again, this is not difficult to follow. You just write everything there. This written step by step. You can see that this is integration 0 to infinity x s minus 1 over x dx. Yeah, 1 over ex minus, so this is our function. And then 1 over ex to minus 1, this is the expansion of those series. Yeah, and then you can proceed that. Yeah, take out the summation, and then you have this, and e minus nx, you can again substitute with some variable, then you can come up with that. So 1 over n to the s, this is the Riemann zeta function, and x s minus 1 e to minus x is the gamma function. Okay. Now another example here. This example require specific knowledge on the complex integral. Right. So if you consider that function, so the mellin transform is defined as that. Okay, so using complex integral to evaluate the integral in the complex plane, so we need to write as to find the residue, where in this case the pole, we have a single pole z minus 1, and that gives you pi over sine pi over s. Yeah, you can refer to my notes regarding the complex integral. Or this is another way of evaluating that. Yeah. So alternatively, you can write, you can evaluate those integral by substitute x with t over 1 minus t, so we obtain that. All right, then after simplification you have this, and then again we identify this as a beta function of order 1 minus s. So which is given as the beta function s1 minus s is the gamma function of s, gamma function 1 minus s, and we can find this as a pi over sine s over pi. Okay, and this is another example that give you the beta function. All right, and then we have basic properties of mellin transform. Yeah, I think it is not difficult for you to prove, so I ask you to prove all these properties. We have given here, I think, 3 properties. So m of f, just substitute a x. With that you can factor out a minus s. You can do this easily, as well as that. And for m prime, yeah, the mellin transform of derivative of function is given by that minus s minus 1 fs. So these are the proof you can see there. So okay, here from here to here, this is just using the integration by parts. Okay, and also we have properties number 4 and properties number 5 is given here. So you just you can prove those things. And the possible formula for the mellin transform. All right. Suppose fs is the mellin transform of fx and gs is the mellin transform of gx. Yeah, so f is a mellin transform, g is mellin transform for g. Then the mellin transform of multiplication of two functions f and g is given by that. So f s g s minus z dz. I think you still remember what is this. This is the convolution of two functions f and g. Provided that f and g is the capital F and capital G is the mellin transform of function f and g. So if you take s equal to 1, right, give the possible formula for the mellin transform. So this is the what we call as a possible formula for the mellin transform. The proof is given here. I don't want to go in detail. You can just follow the proof. I think the proof are written in detail. It's not difficult to follow. You just do it yourself. Yeah. So the above the interchange of order integration requires some suitable condition on fx and gx. I think I'll stop here, and then for the next video I'll give you example on those things. All right, so I just stop here. So what I covered in this video is that we define the mellin transform and the inverse of mellin transform, and also I gave you example of how to calculate the mellin transform given a function, and as well as the properties and possible relation or possible formula for the mellin transform. So in the next example, and in the next video I'll give you example on this thing. All right, bye bye.